Good afternoon, students. So yesterday we discussed about the electromagnetic induction. So in this we have to discuss about what is self-inductance and what is mutual inductance. According to that, which can be followed that one of the application which is related to the self-inductance, that is self-inductance of a solenoid. Okay. So here before going to understand this here, what is inductance means here, which was explained by Henry J. Henry in 1832. That means here, whenever you are to be considering a conducting wire, that should be wounding in a circular uh, 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 shape, so that which contains a number of turns, which is let you assume that capital N is a number of turns, which should be wounding like that in a circular shape. Then you have to say that that is nothing but a coil. So when you are going to be sending the current through that coil, there it can be developed the magnetic field, and or else if you apply a magnetic field to that coil, and it can produce the current. Okay, so that is uh, that was observed by the so many scientists by doing this experiment, and where which was explained by the J. Henry. So that's why here on his name only the standard international units of this coil or the inductance, you can call it as a Henry. Okay, so here let us discuss about the what are the topics we have to discuss, that is related to the 11th unit and final unit. Today we are going to be concluding this, and the last unit is that here what is Faraday's law, what is Lenz's law. Okay, what is the equation for the electromotive force EMFL, all these things. Let me see. So in this self-inductance and mutual inductance here, uh, what is self-inductance? Let me give you here. So if you observe the diagram here, you can able to observe that here a battery is there. Battery means which consists of a positive terminal, and the longer one which is a positive terminal, and the shorter one is a negative terminal of the battery, that is a DC power supply. And in series we have to be considering all these equipments and the components which is to be connected in series. So the positive terminal of the battery which is connected to the coil here, the coil is nothing but a inductance, that is to be denoting here a capital L, and other end which is connected to a key is open here. If you say that if it is open, no current is going to be passing through the circuit here. We are to be constructing a circuit here, and other end of the key which is connected to the galvanometer. So what is the use of the galvanometer? The galvanometer at the center, which is a needle, and if it is to be deflecting towards right and left somewhat, you have to say that here minimum current which is to be measured by using the galvanometer, and the other end of the galvanometer which is connected to the negative terminal of the battery. So this is about the first figure. Okay, and the second figure which is also here a battery positive terminal which is connected to the resistor. Okay, so compare the first figure and second figure. So the positive terminal of the battery which is connected to the inductor here, that is the first one. Whereas for second figure, the terminal which is connected to the resistor, and the other end of the resistor connected to the key, and the key is connected to galvanometer. The galvanometer is connected to the negative terminal of the battery. So what do you observe from these two figures? You can easily observe that one figure which contains the inductor and other coil. Inductor means a coil, and other one which consists of a resistor here. Okay, somewhat. So you have to imagine that which circuit is going to be offering more current. So where here in which circuit you can easily measure the maximum current which is to be allowing through that components. Which one? Can you say that? Yeah, you can easily say that here, the first figure. Why? Because of there is a coil. Coil means a wire. A wire is going to be offering more current. Okay, easily you can measure through the galvanometer maximum current which is passing through the first figure A. And what about the second figure? You can easily observe that there is a resistor. Okay, what is the role of the resistor which is going to be stopping the maximum current, which is not going to allow any current through that component here. That's what here, compared to the figure A and as well as the compared to figure B, you can easily observe that here the figure is going to be offering more current compared to that of the figure B. In figure A, inductor is there, inductor which is offering more current. In figure B, the resistor is there. Their resistor is not going to offer any current at all, which is going to be stopping the current. That's what here. The differences between the coil to the resistor. That means coil is going to be offer more current. Okay. What is coil? A conducting wire. So a conducting wire which is to be here, which is in a circular shape, which contains a more number of turns. Then you have to say that wire is nothing but a coil or a inductor. Is it clear now? Okay. So here you can observe that comparison between the figure A and figure B. What is the self-inductance? The self-inductance phenomena we can easily observe with a coil of many turns wound on a laminated magnetic core. Okay. So let us discuss about these two cases here. So the figure A contains a coil wound on a magnetic core, and from the figure B, the resistor is there. Okay. When two circuits are switched on simultaneously, the galvanometer is going to be showing that how much of the current which is to be passing through that. So, but it is to be noted that the current figure A takes a finite time to grow itself full value, while the current grows full value immediately. Again, when the current is broken, the current it is going to be decreases zero gradually in a finite time, while the circuit it comes to zero immediately. Okay. So that when the key is going to be open here, no current is going to be offering. Slowly the current which is going to be falls down in the case of figure A, and whereas in the figure B, immediately it goes off. That is the case. So the growth of the current through the coil produces change in the magnetic flux, okay, which is linked with the coil. And according to the Lenz law, the electromotive force which can get the induced EMF in the coil. Okay. So and also which is going to be opposing the applied electromotive force. So the induced EMF lasts as long as the growing and decaying. So the EMF induced in a closed circuit which can makes and breaks of the circuit is called the EMF due to the self-induction or the self-induced EMF. So the finite time of growth or decay which can depends upon the here a flux which is linkaged through the coil, and in turn it is also depends on the coil here. So that the coil of the nature and also the shape which is known as a inductors. Okay. More current, more flux is generated. Less current, less flux is to be generated here. When the flux is generated, that is to be linked with the electromotive force is going to be developed. That is the case. What are the coefficients of self-inductance here? Let us consider a long solenoid which contains a capital M number of turns, and also the flux, magnetic flux which is associated with the here. Each turn, that is a 5B, not into B. Suffix B is to be written there. So here, considering to Faraday's law of induction here. The induced EMF which can given by E equals to minus d by dt of n phi b, where capital N is to be indicating that the number of turns, and phi b is indicating that the magnetic flux linked with that circuit, E is the electromotive force. Okay. So, and also n phi b, that is which is linked with the here flux here, so that n phi b which is proportional to the here current I. Okay, phi b is proportional to I. Why? Because of here, due to the current is only the flux is to be generating. That's why here when more current, more flux, less current, less flux. That's why n phi b is proportional to the I here, or else n phi b equals to Li, where L is the proportionality constant. This you can call it as a self-inductance of the coil. Okay. So comparing these two equations here, so in place of EMF E equals to minus d by dt of what is n phi b value, simply you can substitute Li. Okay. So here L into E equals to minus L into di by dt. Or if you want to write it down, the equation for the self-inductance of a coil, capital L value minus E by di by dt. So what is the units for this inductance? Henry, or else 1 volt second per ampere. Next, what is the mutual inductance of a coil here? So mutual, when you spoke about the mutual here, it needed two coils. One is the primary, another one is the secondary here. Okay, now let us discuss about from the figure here. You can easily observe that what is the figure which is to be indicating here. There is a battery, so two batteries, three batteries are there. Okay, DC supply, and there is a key, and in series a coil is to be connected. That means this is a primary coil. Beside of the primary coil, secondary coil is there. In this secondary coil, in series the galvanometer is to be connected. So what is the thing which is to be happened here? Whenever the key is to be closed here, the current is to be passing through the primary coil. Whenever the current I is to be passing through that, the magnetic flux is to be generated. So when the magnetic flux which is to be changing here in secondary, the current I is to be generated. That should be measured by using the galvanometer by deflection. Okay. So this is the case which is to be takes place here. Primary to secondary as well as the secondary to the primary here, vice versa. So that's what here the demonstration of the mutual induction by the two coils, one in another. So if the primary coil is offering a current, there is a flux. That flux is to be changes. The induced EMF is to be generated. Whenever the induced EMF is generated, the current I is to be generated. That is linked with the magnetic flux. Yeah. See here. So you know pretty well here. What is that here? Di by dt of n into phi b, which is nothing but a m into di by dt, and also minus E equals to m di by dt, and where m equals to minus di by dt. In the case of m is the mutual inductance of these two coils, where L is the self-inductance of the single coil. So L and M. So both the equations are same, but one thing you have to remember that for the self-inductance is only one coil is there. For mutual inductance, two coils is to be considered. So for self and as well as the mutual inductance, the units of these two is Henry only. Okay, that is the case. Next, how to calculate the self-inductance of a solenoid. Okay, solenoid, what is solenoid? By considering a rod, on that rod, if you are going to be here wounding the wire in a number of turns, that setup which is nothing but a solenoid. So toroid means toroid which is in the shape of a ring here. Okay, On that ring, if the wire is to be wounded in n turns, that is related to the toroid. So this is the solenoid here. So to calculate the self-inductance capital L value, so L equals to N phi B by D I. That is, you already know that. So let us consider the solenoid which is having a number of turns, small number of n number of turns per unit length. But the length of the coil is small l, and the area of cross section is capital A, and the flux linked with that coil is nothing but n phi b equals to here NLBA. Okay, so where NL is the here total area here, and BA magnetic flux, and A the area of cross section. Okay, you know pretty well B equals to mu naught NA. Why? Because of this is the magnetic induction value for a solenoid, which is related to the here magnetostatics. So by combining these two equations, by substituting in place of B value n phi b equals to NL into, in place of B we are writing here mu naught NIA. Okay, so what is the value here? N phi b equals to n naught into, that is a mu naught, not n naught, mu naught into n square LIA. Print mistake is there, you can correct it in ninth equation, this one. This equation, this is not n naught, this is mu naught, you can see here. Okay, na? Print mistake. Therefore the self inductance of a solenoid, you know the formula for that, L equals to n phi b by I. B is the suffix here. What is n phi b? Mu naught. There is no mu naught is written in that equation, you can correct it. Mu naught n square LIA divided by I get cancelled. What is the remaining portion here? Mu naught n square LA. Thus the inductance of a solenoid which is having a length which is proportional to here its volume, that is L into A, and to the square of the number of turns per length. Okay, square of the number of turns per length, and here which can depends upon the geometrical factors. So what is the summary of this? What is the summary which is related to the here? So what is the coefficient of the self-inductance? That is small e. E is nothing but electromotive force, equals to minus L di by dt, or else L equals to minus E by di by dt. Next, coefficient of mutual inductance, M equals to minus E by, E is electromotive force divided by di by dt. So what is the equation for the coefficient of self-inductance of a solenoid? L equals to mu naught n square L. So you have to imagine that there should be a problematic questions which is to be asking to you. You have to aware of it. So check your answers. What is that? When the changing current flows through a conductor, the changing magnetic flux surrounding the conductor should induce EMF within itself, that is in the conductor itself. So this process or the phenomena which is known as self-induction. So what is the units of the self-inductance or the mutual inductance, which is a Henry. Next, what are the model questions which is to be given? Let the derive the expression for the coefficient of self-induction and mutual induction. Next, derive an equation for calculation of inductance of the solenoid. What are the short questions? What is self-induction? Explain. With the diagram only you have to explain. Next, what is mutual inductance? Explain or discuss. So these are the problems which is to be given. And also worked exam. Let me say you here. See here. A 10 Henry inductor carries a Henry. Okay. Henry means inductance value is given here. L value. Henry inductor carries a steady current of 2 amps. I is also given to you. Okay. How can I 100 volts self-inductance EMF value is 100 is given, be made to appear in the indicator? So you know that E equals to L di by dt, and E value is 100, L value is 100, di by dt. So here by doing this calculation, 10 amps, di by dt value is 10 amps per second. So for self-inductance of a solenoid, that is also to be calculated. So you can follow that mu naught n square LI. L equals. So you need to know about that what is self-inductance. The EMF induced to oppose any change of the original current in this coil. This is a self-inductance. So what is the phenomena of mutual inductance? The phenomena of producing an induced EMF in a coil due to the change in the magnetic flux in it if a nearby coil is called mutual induction. Next, last one, 12th unit. Here Faraday's law and Lenz's law. So in this, you must aware of the Faraday's law and Lenz's law. Why? Because of in electrostatics gas law, surface integral E dot ds equals to Q by epsilon naught. Okay, that is the one of the Maxwell's first integral form equation. What is the second one? In magnetostatics, surface integral B dot ds equals to 0. Next, the third one is in magnetostatics, here Ampere's law. Okay. So that is the fourth equation. Third equation is for Faraday's law. So the line integral E dot dl equals to minus d phi v by dt. Fourth law, line integral B dot dl equals to mu naught into I. So here Maxwell is also, that is also to be corrected here. What is the corrected Ampere's law? Okay. So those four equations. That means electrostatic, gas line electrostatics, gas line magnetism, and Faraday's law, and finally Ampere's law. These four equations, which are Maxwell's equations, okay, which is in integral form. So that is also to be converted into a differential form. That is the most important essay question. Okay, now? So you can aware of these equations. Let me discuss that what is Faraday's law, what is Lenz's law. What is electromagnetic induction? So this is an empirical principle of the Faraday's, and let us consider that a surface of area which is bounded by a copper wire and which is placed in a magnetic field capital B, and the flux, magnetic flux, which is passing through the area capital A, which is given out here, phi b equals to surface integral B dot ds. Okay, so that is the equation. And where small n, which is in the above equation, is a unit vector which is normal to the surface. So here the flux is taken as a positive, and when the normal points outward direction. So when the normal points in the opposite direction, the value angle theta value should be considered 180 degrees. Okay. So see here, there is a magnetic flux. Inside the magnetic flux, if you choose a Y, which is a closed loop here, so that loop which is to be here a normal vector which is kept small n, and the flux, the line of force of magnetic flux which is indicating the arrow whites, arrow lines here, that is a capital B, and a infinitesimal area which is occupied by this loop is a ds here. By integrating the ds, you will get the what is the area capital A here. Okay, the capital A which is linked with that here, the total area of the loop which is occupied by this. Okay, so how many of the lines which is passing through the infinitesimal area ds, and where the direction which is perpendicular to this, then that is called here a magnetic flux phi b. Therefore, with respect to the equation portion, phi b equals to surface integral b dot ds. That is the case. Let me explain you how the magnetic flux and which is linked with that coil here. So by considering in first figure, you can see that there is a bar magnet, that is which consists of south and north poles. The downward arrow mark which is indicating that you are going to be moving the bar magnet towards the coil, and below there is a coil here, the coil which consists of a number of turns which is wounding there in a circular loop, and the two ends of the coil which is connected to a galvanometer G here. Okay, so whenever the bar magnet which is moving downwards towards the coil here, okay, what will happen here? So the when you consider a bar magnet, due to the magnet here, the magnetic field is to be developed. That means you are applying the magnetic field to the coil. So what will happen here? Whenever you apply a magnetic field to the coil, there is a induced EMF is to be generated here. Due to that induced EMF, the small deflection should be takes place. That deflection indicating that a small amount of current is to be generated in the coil. That's it. Okay. By moving the bar magnet towards the coil, the current induced current is to be generated in the coil, and it is to be measured by using the galvanometer G. Is it clear now? Next, what is the other figure? A standardized fixed bar magnets are there. Magnet is there. The permanent magnet is there. And the previous figure is a bar magnet. You are to be moving towards the coil in and out. But whereas the figure B is a permanent magnet is there, and a coil is there. The coil which is connected to the galvanometer. So in this also, here you can easily observe that what is the current which can appears in the experiment above that, which is called the induced, and which is said to be here set by an induced electromotive force. Okay. Next, most important question is that what is Faraday's law? What are the Faraday's law, and what is the integral form of the Faraday's law, and what is the differential form of the Faraday's law? You can easily observe. Okay. Let me say you here, there are two laws are there for electromagnetic induction. So first law is that we see here, I am going to be reading here, you can observe that what is that law and what is that equation here. Whenever the magnetic flux which is linked with a closed circuit. What do you say? Whenever the magnetic flux, okay, magnetic flux means YB equals to surface integral B dot ds. Okay, Randy. So which is with a closed circuit, linked with a closed circuit, and changes in the induced EMF, and it is set up in the circuit whose magnet at any instant which is proportional to the rate of change of magnetic flux, which it linked with this circuit. Therefore, EMF equals to minus d phi by dt. Negative sign indicating the decrease of the flux with the induced EMF. Phi is the magnetic flux linked with the circuit. So this is about the EMF equals to minus d phi b by dt. Only the negative sign, which is nothing but a Lenz's law. Okay. So here the direction of the induced EMF is such that it opposes the change in the flux. Getting my point? Again, I am going to be reading here. The direction of the induced EMF is such that it opposes the change in flux that produces it. So this law, which is known as Lenz's law, and through the direction of the induced EMF, which was determined by the Faradays, and it was explained and it was expressed on the as a law of Lenz. So what is the law expressed mathematically? E equals to minus d phi by dt. E is the induced EMF, phi is the flux. So to explain the Faraday's law of electromagnetic induction, let us consider that coil and magnet in the experiment. So here, when the bar magnet is to be considered, a bar magnet which is moving towards a coil here, a north pole. So the more number of lines which is passing through the coil, that means we have the more flux is to be generated. That means the induced EMF is to be increases. Okay. If the magnet is moved towards the coil, the flux value increases, while if it is moving away from that, the flux is to be decreases. So in this way, the EMF in the induced EMF, which is here, changes according to the motion of the magnet. So greater motion of the magnet, which can increases the greater in the rate of the change of flux. Less means less one. So the induced EMF is directly proportional to the rate of change of magnetic flux, which is linked with the circuit. Okay, Nandi? So mathematically, how do you express it? EMF value is equals to minus d phi b by dt, and you know that what is phi? Phi is the magnetic flux. So the value is surface integral b dot ds. Substitute there in a above equation. E equals to minus d by dt of phi b plus surface integral b dot ds. Okay, but you know that E value is by line integral E dot dl. Okay, EMF equals to E dot dl, not a b dot dl. Okay, Randy. Therefore, the print mistake is there. B dot dl equals to minus d by dt of B dot ds. But left hand side there is a line integral, and the right hand side section which contains the surface integral. So if you want to change the line integral into a surface integral, from the vector analysis we have to be considering that the Stokes theorem, so which can allows that, which can convert that the line integral can easily change into the surface. So that the line integral E dot dl equals to here the surface integral curl E means del cross E ds. Substitute in above equation. Therefore, surface integral curl E ds equals to minus d by dt of here b dot ds. So left hand side and right hand side both are surface integral. You can remove it. So that after that you can have curl E or del cross E equals to minus dB by dt. So this is the integral form of the, this is the here differential form, not a integral form. What is this? This is the differential form of the Faraday's law. Okay, integral form means minus E equals to minus d by dt of here integral b dot ds. That is integral. So that you can convert into a differential form. Okay, so correct all these. So many mistakes are there. Okay, so many print mistakes are there. Don't be right that this is not a integral form. This is the differential form of the Faraday's law. Next, Lenz's law. What is Lenz's law? Here you know that this is the Faraday's law. Phi equals to minus n into d phi v by dt. Okay. Here n is the number of times negative sign indicating that here the direction on which the induced EMF is to be acted. Okay. So here the induced EMF which is always acts in such a direction that it is to be opposing the charges causes it. So this is a consequence of the law of conservation of energy, and which is to be predict that here the direction of the induced EMF, and you have to consider that a simple experiment, a single coil or a bar magnet, let the north pole of the bar magnet, which is to be moving towards that bar magnet is suddenly pushed towards the loop, induced EMF for the voltage which is to be developed in the loop, and the induced EMF set its own magnetic field around it, and thereby it behave like a magnetic dipole. Okay, being a north pole, the opposite face being a south, and like that you have to follow that. You can write it down. So from this experiment only you have to conclude that here the right hand rule is a south pole and the current must be in opposite. Okay, whether we will push or pull, the magnet its motion is always automatically opposed. Next is that expression for the induced EMF. So this is a north and south, a permanent magnets are there. A coil is there, a coil which is connecting in a series, a galvanometer, which is moving towards that. There is a current is to be passing through that. If you move upward and downwards like that here, how the deflection is to be changed takes place, that is to be observed, and you have to derive the equation part of that also. What are the time varying magnetic fields? What is that? Time varying means how the magnetic flux which is to be changing with respect to time, d phi by dt value, E value, time varying magnets value. Yeah, you can see here, according to the Faraday's law, E equals to minus d phi by dt value. By substituting E value is line integral E dot dl equals to minus d phi by dt. Okay, so here a changing magnetic field which can set up an electric field in this space, and there a great deal of an evidence which is support of the view of the Faraday's law in induction, and also which is an important type of a particle accelerator which is called as a betatron. Okay, so what is that use of the betatron? You can easily accelerate the here acceleration of the particle. That particle is to be considered as a electronic here. There only we are to be using this operation, and the existence of the field quite independently of any conducting wire. Okay, Nandi? So check your progress. What is the state of Faraday's law of electron? Next, moving coil galvanometer. Okay. So here, this is an also question here. Here, which is an instrument which the magnetic effect which is used to measure and detecting a current or a electric charge which is called a galvanometer. And there are several types of galvanometer, which is depends upon that construction of specific purpose. A current carrying conductor moves with when placed in a fixed permanent magnetic field, which are called the moving galvanometer. So this is used to measure the momentary currents. And a moving coil galvanometer, which consists of a flat coil of insulated wire, which is suspended between the poles of permanent horseshoe type. You can see that. Okay. Magnets, usually the coil is suspended by a phosphor bronze wire. Okay. So more field is there, more current is there, more twist should be takes place. Less is there, less twisting is to be takes place. So that this is proportional to that here. That means a torque tau is to be acting on that by twisting, or the deflection to be takes place by this. So tau equals to B N I. Like that you have to derive the equation portion. Okay. So only 5 minutes are there. So here, what is the damping correction? This may be asked as a short question to you. Okay, you can go through that. What is the summary? The summary is a relative motion between a conductor and the magnetic field, which increases, will induces an EMF in the conductor, and the direction of the induced EMF, which can depends upon the direction of the motion of the conductor with respect to the magnetic field, and the magnitude of the EMF which produces, and which is directly proportional to the rate of change of magnetic flux. E equals to minus d phi v by dt. Okay, like that. Check your progress. What are the Faraday's laws of induction? Two laws are there. You have to write it down. And what are the questions which is to be giving to you? Check it once. Describe the Faraday's law of induction. Lenz's law to explain the induced EMF. And a working principle of a moving coil galvanometer. Okay, short questions is that what is time varying magnet? And explain induced current voltage. That means EMF in a load. Okay. So this ends our syllabus. So this is the question paper. How the question is to be given to you. Electromagnetism. 80 minimum is 32 marks. 4 into 10, 40. And objective it's 20 into 120. Like that. Fill in the blanks is there. Objective questions is also there. Correct. So this ends our syllabus here. So by coming class, we will discuss about that. This ends our here DSC paper, and elective paper. It is only 4 classes. Okay, for 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 that 4 classes, we have to conclude the elective paper. Okay, Nandi? So prepare well. If you have any doubt, please ask me regarding this. Okay, write all the best.